with Ricci bigger than or equal than rho. Rho any real number. Then for any two functions C1 functions A from 0 to 2. So remember, A has to be non-negative, and gamma can be anything. One has so A times 5 prime bigger than or equal than A prime plus 2 rho A minus 4 A gamma over n times 5 plus 4 A gamma over n times Laplacian of PTF. Everything is evaluated at a fixed point x here, minus 2A gamma squared n. I mean a fixed but arbitrary point x. Okay, so I'm going to be using this result again now. And so remember the theorem that we were discussing yesterday was the following one. So let M be n-dimensional complete, and let's say Ricci bigger than or equal than 0. There is a substitute theorem if Ricci is bigger than or equal than rho. So I just stated in this case because all the ideas are already in this theorem. Then once you see the ideas here, I think that with a little bit of work you can easily generalize this to the case of Ricci bigger than or equal than rho. Then there exists Cn bigger than 0, a universal constant, such that for any x in M, any r bigger than 0, the volume of the ball centered at x with radius 2r is controlled by Cn times the volume of the ball centered at x with radius r. So that's a theorem that we wanted to prove. And we saw that the proof of this theorem via the Harnack inequality that we have already proved as a consequence of the Liao inequality, which follows from here. So only Bochner's identity has been used so far. So the proof of this theorem was a consequence of this theorem here. So everything boils down to this main result that I'm about to prove now. So again, M as in previous theorem, we want to show that there exists absolute constants k bigger than 0, then 0 less than a less than 1, such that for every x in M, for every r bigger than 0, one has that the heat semigroup evaluated at time a times r squared with the initial value, the indicator function of the geodesic ball centered at x with radius r, evaluated at x, is bigger than or equal than k. So let's call this theorem 1, let's call this theorem 2, and theorem 3 in this lecture, just for ease of reference. And yesterday I have observed that theorem 3 implies theorem 2. Okay? So we saw yesterday that this theorem here implies this theorem via some standard considerations.
Excuse me, but this constant k, a, depend on dimension or not?
They depend on dimension. Absolute constants for me are, you know, constants which depend on dimension. Okay. So at this point, in order to complete the proof of theorem 2, we need to show theorem 3. Okay, and this is what I'm going to be doing now. So, proof of theorem 3. I'm going to deduce theorem 3 simply from theorem 1. Remember that theorem 1 is just some clever workout with the Bochner's identity. So I'm going to show that I'm going to deduce theorem 3 from theorem 1. Well, life is not so easy as I am saying. I mean, you have to do some work. So, but the main step will be using this inequality here with a clever choice of function A and function gamma. So I'm going to be taking a fix at this moment tau arbitrarily and consider function A of t equal to tau plus capital T minus little t. Very simple choice. Okay? Notice that I'm assuming that Ricci is bigger than or equal than 0, so rho is 0 for me. The lower bound on the Ricci tensor is 0, so this is not here. Rho is 0. I mean a special case of this theorem when rho is identical equal to 0. Of course, you can treat the case of general rho as I said. It doesn't matter, but it just complicates a little bit the calculations, and it's not worth doing it. Okay. So now we choose gamma such that the enemy, which is the quantity between bracket here, because I don't have any control of phi, so the enemy is 0. So A prime minus 4A gamma over n is identically equal to 0. So that means that I have to choose gamma. You will trust me with this choice of A. You just solve for gamma here and you compute the gamma is minus n over 4 times 1 over tau plus t minus little t. Okay, just a simple calculation. So in this case, we have clearly we have A prime identically equal to -1. So let me compute some of the quantities that come into this thing. So A times gamma. Now we know A and we know gamma. So you can check that A times gamma is minus n over 4. And that the other quantity involved is this one. So minus 2 A gamma squared over n is equal to minus n over 8 tau plus t minus little t. Okay, so we have all the ingredients now to apply the theorem. So apply theorem 1 and integrate star on interval 0t. So in the left hand side we get A of capital T, phi capital T minus A of 0, phi of 0, bigger than or equal, then so this object is gone, because I've chosen gamma so that this is 0. And then I get plus 4a gamma over n is negative 1. So I just get minus Laplacian T F, Laplacian PTF. And then we get minus 2a gamma squared over n. So minus n over 8 tau plus t minus little t times PTF. Remember, everything is calculated at a point x, fixed point x. Notice that a of capital T is equal to little tau, and a of 0 is equal to tau plus capital T. Okay? So let's also remember that phi of t is pt of pt minus pf times gamma log of pt minus pf. So from the expression of phi, we immediately see that phi of capital T is equal to P capital T. So here I pick up F, and here I get gamma or log. So when T goes to capital T, I get the initial value log of F. Whereas phi of 0, so when t goes to 0, I pick up the initial value of this function from here, from the semigroup. So I get PTF gamma log of PTF. Okay, so now I replace this information in there, and I get, so I get tau times phi of capital T, which is PTF gamma of log F, minus A of 0, which is tau plus capital T, phi of 0, which is PTF gamma log of PTF. So this is bigger than or equal of minus Laplacian of PTF minus n over 8 tau plus t minus little t PTF. So this is the basic information which we get from theorem 1. Okay. At this point, I want to apply, so this is theorem 1. With a special choice of the function a, and with a choice of the function gamma, such that this quantity between parentheses is 0, so I can throw away the part with phi. Phi is the enemy in general, at least in this theorem here. And it was the enemy also in the choice of the Liao inequality. All right, so this is the basic inequality. Now I can erase everything else, I guess, because I will need space. I don't need anything else. Remember, the only thing that we have to keep in mind is that we want to end up with this information here. So let me erase theorem 1. We have used it. let me erase theorem 2, because we have already observed that theorem 3 implies theorem 2. So we only need to prove theorem 3. And I guess we can also erase everything else on this blackboard, because all we need is what we have here in the box. Remember that tau is arbitrary at this moment, and you will see later on that I'm going to optimize my choice of tau at some point. Okay. So I want to apply now this inequality here with f replaced by e to the lambda f, where lambda is a number bigger than 0, and the f is a globally defined Lipschitz function on M, which is also in L infinity of M. By some limiting process, you can see that the inequality continues to be true for these functions. Because notice that if f is in L infinity, this function is going to be in L infinity as well. And it's going to be Lipschitz. Okay? So I just ask you to accept that I can replace in this inequality function f. Remember, f was initially here, f was a C0 infinity function bigger than or equal than 0. I want you to accept that I can replace a C0 infinity function with a function of this kind, where f is Lipschitz and L infinity. And of course, it's automatically bigger than or equal than 0. Okay? So if I replace this in here, notice that the logarithm, so here I have logarithm of f, but f has been replaced by this, so I get lambda f, okay? So if I take gamma of the logarithm of this function, so gamma of the logarithm of e to the lambda f is going to be equal to gamma lambda f. That is equal to lambda squared gamma f. Remember, gamma is the inner product of the gradient with itself. So we get the square. Okay. So after we do all these calculations, well, all right, so let me also make now another choice. I'm going to set psi of lambda t equal, this is my definition of psi of lambda t, this is going to be equal to 1 over lambda times pt of e to the lambda f. Okay. Is that what I want? Yeah, that's what I want. So let's observe that pt of e to the lambda f is going to be a function which I choose eventually. Okay? At some point I will choose f in a special way. So pt of e to the lambda f is going to be equal to lambda psi. Something is not right. Something is not right here. Just give me 1 second. Let's see, what do I want in the end? Maybe it's much easier to work here with this function. So I want this to be e to the lambda psi. That means that I have to take the logarithm. So let me take the logarithm here. 1 over lambda times the logarithm of pt. Okay, so I define function psi in this way. All right? So once I decide f, psi is decided by this equation here. Okay, so with this choice, then I have that pt e to the lambda f is e to the lambda psi. Very good. So now let's see, what do we get here? So here we get from here. So let's call this inequality double star. So from double star, we obtain, so we obtain tau lambda square pt of e to the lambda f gamma of f. I already observed. I'm replacing f with the, you have to think that I'm replacing in this inequality f with e to the lambda f. And therefore, this term here becomes this. Okay? So then we get minus lambda square again. So we get p plus tau. So here I have pt of e to the lambda f, so we keep it. Pt of e to the lambda f is e to the lambda psi, so we get this. So this guy here has to be replaced by pt of e to the lambda f. But pt of e to the lambda f is e to the lambda psi. So now capital T is playing the role of little t here, so it will be, I will switch from little t to capital T. It's a fixed t. Okay? So I get this thing here. So then I get here gamma of psi. Okay? Notice that a log of pt, f has to be replaced by e to the lambda f, so the log is lambda times psi. So I get a lambda coming from here, and then I get another lambda coming from here, and so I get lambda squared here. So this is bigger than or equal. Then let me see one thing here. I think that somewhere...
You didn't integrate it.
Yeah, somewhere we lost something. I remember I was integrating between 0 to t, so I get the t here. Okay? And I also integrate this guy from 0 to t, so we get the log. So let's correct this. So we get minus n over 8, and then I get the log of 1 plus capital T over tau. Okay? So now everything is correct. Remember that I have to integrate between 0 and capital T. So this is a constant. This is a constant, but when I integrate, I get capital T here, and here I get the log. All right, so so here we get bigger than or equal than minus t times Laplacian of pt of e to the lambda f minus n over 8 log of 1 plus capital T over tau, and PTF gets replaced by PT e to the lambda f, which is e to the lambda psi. E to the lambda psi. Okay?
Didn't we lost tau
Let's see, where? Where did we lose tau? We didn't lose any tau, I think. This was tau plus capital Tau divided by tau. So I write it like this. Okay? But I don't think we lost anything at this point. I think that this is fine. All right. So now I'm going to choose f also. I'm going to impose a further condition on f, that the length of the gradient of f be less than or equal to 1. All right? So this is a condition that I'm imposing. So when I choose f at the end, I have to make sure that it satisfies these requirements here. So since I have gradient f less than or equal to 1, then I make the observation that pt of e to the lambda f times gamma. So this is less than or equal. This object is less than or equal to 1, so pt is increasing. This function is non-negative, so I get this is less than or equal than pt e to the lambda f. And pt e to the lambda f is e to the lambda psi. So this is just a simple observation to tell you that I can continue this inequality from here, from above, if I replace this term with this term here. Okay? Because this term is bigger than this, because of the choice that I'm making on my function f. So, moreover, let me make another observation. I know that the Laplacian of pt of e to the lambda f, so this is equal to ddt of pt e to the lambda f, right? Because pt of this satisfies the heat equation. And pt e to the lambda f is equal to e to the lambda psi, so this is equal to ddt of e to the lambda psi, which is equal to lambda e to the lambda psi d psi dt. Okay? So I made that observation just to tell you that I'm going to replace this object here with this object here. So in this inequality here, capital T or little t are, you know, they are just a fixed t. So just now switch again from capital T. So here, in this inequality, switch from capital T to little t. And then let's apply these two observations here. So what we get is t lambda squared. And then, as I said, I'm going to replace this with this from above, e to the lambda psi. Then I have minus lambda squared tau plus capital T e to the lambda psi gamma of psi bigger than or equal than so we get lambda squared t plus tau e to the lambda, let me see, so I have this thing here. Well, why don't I keep, let me see. So let me replace this thing here. So I get minus lambda t e to the lambda psi t psi dt. So I've replaced this term here. And then I have minus n over 8 minus n over 8, and then I have log of 1 plus capital T over tau, and then I have e to the lambda psi. Okay, that is fine. So now let's rearrange this inequality. I'm going to take it to the left-hand side, the term with dip psi dt. So what we get from this inequality is dip psi dt bigger than or equal than, well, you know, I'm going to write just the result. You have to take this, so take this over here, take everything over there, divide it by this quantity here through, and then you see what happens. Okay, so what we get in the end is lambda 1 plus tau over t times gamma of psi minus tau lambda over t minus n 8 lambda t log of 1 plus t over tau. Okay? So this is what we get from this inequality here. Okay, very good. Now, I just make a trivial observation. Gamma is always bigger than or equal than 0 because this is the Carré-Duchamp, is the length of the gradient squared of this thing here. This quantity is positive, lambda is positive, so I just throw this away. The inequality continues to be true. Right? I've thrown away a positive quantity, so I continue the inequality. Okay, so, and I'm going to rewrite this as, so dip psi dt is bigger than or equal than minus lambda over t. So then I get, so minus lambda over t, I get tau, which comes from here. Then I have plus n over 8 lambda squared, log it, of 1 plus t over tau. So I get that dip psi dt is bigger than or equal than this. Okay, at this point let me call, so let's call, remember that this inequality here at a fixed x and t is true for every tau bigger than 0 because tau was arbitrary. Okay? I'm going to optimize tau now. So this is true for any tau bigger than 0. Now I'm going to choose the optimal value of tau. So here this is independent of tau, so I can take the maximum here in tau and that the inequality is still true. So let me, I think I want to keep this guy here, but we can erase everything else. And remember that I guess that I can erase this stuff here, I can erase this stuff here, but let's keep in mind how I've chosen my f. Okay, so now let me call h of tau the function which I have between parentheses here. So tau plus n over 8 lambda squared log of 1 plus t over tau. T is fixed, tau is the variable here. So I guess that this function attains its maximum at point tau, I mean this is a little calculation, which is this one. I will not compute the derivatives because otherwise I will get it wrong, so just trust me that tau max is this guy here. And then h tau max is going to be equal to an expression, which I'm going to write here now. T over 2 times the square root of 1 plus n over 2 lambda squared t minus 1. So then we are plus n over 8 lambda squared, and then I have the log of 1 plus 2 over the square root of this quantity minus 1. Okay? So it's clear from here that d psi dt is bigger than or equal, continues to be bigger than or equal than minus lambda over t times h tau max. Okay? So, in conclusion, we get that minus d psi dt is less than or equal than whatever we get, so it's lambda over 2. You know, I have to multiply this by lambda over t, so I've taken minus here, less than or equal, lambda over t times that thing. So what we get is lambda over 2 times square root of 1 plus n over 2 lambda squared t minus 1 plus n over 8 lambda t log 1 plus 2 divided by the square root of 1 plus n over 2 lambda squared t minus 1. I will write the function in the right hand side for a reason that you will see in a moment as lambda times g evaluated at 1 over lambda squared t. And my function g, so g of s, is the function 1/2 square root of 1 plus n over 2 times s minus 1 plus n over 8 times s times the log of 1 plus 2 over the square root of 1 plus n over 2 s minus 1 close parentheses. So take lambda out, whatever is left here, call it g evaluated at lambda squared t. So in order to force the lambda squared t here, you have to put a lambda here. So you put lambda here, lambda squared, and then your function becomes that one. Okay? So there are two important things. First of all, it's obvious from the way I've defined g, g goes to 0, 0. This guy goes to 0, this guy goes to 0. So g of 0 is 0. But then, even more importantly, g of s behaves like the square root of s as s goes to plus infinity. Okay, this is easy to see. This thing here behaves like square root of s at infinity. Okay, and so that is the dominant behavior. I mean, you can check it very easily by Taylor's formula. Okay, so we know that at infinity, g behaves like this. This will be crucial for the finishing of our proof, this information here. All right, so now let's go back to what we had before. So we had minus d psi dt less than or equal than that. So I'm going to integrate now this between S and T. So I integrate this inequality. We're almost finished.
You mean inequality here, not equality.
No, inequality, inequality. Thank you. So let's integrate it between S and T. So we get psi at S minus psi at T. So I'm going to write it like this. Psi lambda S less than or equal than psi lambda T plus lambda integral between S and T of G of 1 over lambda squared tau d tau. And now let me make a few considerations. First of all, lambda psi is written here is equal to the log of pt e to the f, e to the lambda f. I'm going to apply Jensen's inequality, integral form. So if you have a convex function and you take an integral, so phi of the integral is less than or equal than the integral of phi. So my convex function is minus log. Okay, so I'm going to apply Jensen's inequality to minus log. So the inequality goes into a certain direction. Since I have log, I have to switch the inequality. So this is equal to log, so by Jensen, so this is where I apply Jensen's inequality. By Jensen, this is bigger than or equal than pt log of e to the lambda f, which is equal to lambda ppf. So the observation which I make is that lambda psi is bigger than or equal than lambda ppf. Therefore, psi is bigger than or equal than ppf. Okay? So that means that here I can go this way if I put PSF. So I have PS lambda f less than or equal than psi of lambda s by the observation which I've just made. Okay? And then I know that psi of lambda s is less than or equal than this stuff here. So this is less than or equal than psi lambda t plus lambda integral between s and t of g 1 over lambda squared tau d tau. Okay, very good. So forget about the intermediate step. So we know this now. Let me let s go to 0. If I let s go to 0, I pick up the initial value by the semigroup property. Okay? So letting now let s go to 0. So we get lambda f less than or equal than psi lambda t plus lambda times the integral between 0 and t of g 1 over lambda squared tau d tau. Okay? Right. There is, did we have a lambda floating around here? So there was this guy here. Okay, so we're fine. Well, at this point we make the choice, so at this point we choose F. So let me tell you how. I'm going to erase everything now because I won't need this stuff anymore. So now I'm going to choose F. So up to now, so now I choose F. And I take F of y to be the function equal to minus the distance between y and x if dyx is less than r and equal to minus r if dyx is bigger than or equal to r. So this is a cutoff with a constant of the distance function. Distance function is Lipschitz on the manifold, okay? And since outside of a compact set, by the way, I'm taking a manifold to be complete, so by the Ofrinov theorem, every geodesic ball is relatively compact, okay? So the closure of a ball is a compact set. Outside of a compact set, I'm modifying f with a bounded function. So f is Lipschitz and in L infinity. And the gradient of f squared is less than or equal to 1 because distance function satisfies the aconal equation and it's 0 outside of a compact set. So this is true also. Okay? So I can use that f in my inequality. This f is fine. Okay, so now let's see what happens with the choice of this f. Oh, maybe I don't need this. All I need is this now. I can erase this one too. I can erase this one too. I can erase this. And I can erase this because I've already... Okay. So let's denote for simplicity B, the ball centered at x with radius r. So then we have e to the lambda f, this is equal to, or actually less than or equal, and you can check easily that this is true, e to the minus lambda r times the indicator function of the complement of the ball plus the indicator function of the ball. Just take any arbitrary point on the manifold and put it in this inequality and check that the inequality is true. I mean, it's trivial from the way I've defined it. Okay?
What does mean b squared?
B complement.
Complement.
So this function is 1 in the complement of B and 0 inside B. Okay. So therefore, with this choice of, once I choose F, then by the equation which I have erased, I have chosen also psi in a way. So anyhow, but I'm going to take now, I'm going to make some elementary consideration. E to the lambda psi lambda t evaluated at x. Lambda is a function which depends also on x, because remember, e to the lambda psi is equal to pt e to the lambda f. So when I evaluate this at x, then it means I'm evaluating this lambda, which depends on psi, which depends on lambda t at point x. So lambda, e to the lambda thing, so this is equal to pt e to the lambda f x. And since I have an estimate for this, this is going to be equal to, less than or equal to e to the minus lambda r times pt of the indicator function of the complement of the ball, evaluated at x, plus pt, indicator function of the ball, evaluated at x. Now on this guy, I have 0 information. So I'm going just to bound it by 1. So this is just going to be bounded by 1. And remember, what is our objective? Our objective is to prove that the PAR squared 1 over B x is bigger than or equal than a constant. Okay? So now, for the first time, you see what we want. It's here. This goes now to the left-hand side. And so the information that we have at this point is, let's see, I can erase everything except this inequality here. So the information that we have, let's see, I think it's fine. And this is fine too. This is fine too. Right. So what I have now is this. The PT of the indicator function of B evaluated at x is bigger than or equal than e to the lambda psi lambda t x, which is here, minus e to the minus lambda I. And this is true for any lambda bigger than 0. As you will see now, I'll make a special choice of lambda and a special choice of little t. So to estimate this term here, I do this. So 1 is equal to e to the lambda f x. Are we all convinced of this? If I evaluate this function in x, I get 0. Okay? So e to the lambda fx is 1. Because I'm evaluating at the center. Now this is where it becomes crucial, that I'm at the center of the ball. Otherwise I lose control of everything. Okay, so I get 1. And then this is less than or equal. Then e to the lambda psi x t x times e to the capital phi lambda t, where capital phi of lambda t just comes from whatever I add, whatever I add, no, it's still here, okay? So, so this capital phi is just lambda squared integral between 0 and t g of 1 over lambda squared tau d tau. Okay, so this tells me that e to the, so this inequality here implies that e to the lambda psi, this is lambda e in x is bigger than or equal than e to the minus phi lambda t. Okay, so in conclusion, we have reached the conclusion. Let me see, where can I erase? I can erase this thing here now. I hope. In conclusion, oh, good, it's here. So I have this inequality here. In this inequality, I'm going to estimate from below this object with this one. So let me write it here. I reached the conclusion that pt of 1b x is bigger than or equal than e to the minus 5 lambda t minus e to the minus lambda r. Which one is our friend in this inequality? our friend in this inequality is essentially lambda. Lambda was an arbitrary positive number, and in a way also t, although we don't have much choice, right? We want t to be a times r squared in the end. Okay? So we want t to be a suitable multiple of r squared. Okay, so now I make my choices of lambda and t. So at this point we are really almost finished. But remember this thing here. So at this point we're going to choose t and lambda, and I'm going to be taking t as a r squared, and I'm going to be taking lambda as 1 over r, so that this quantity becomes a constant. Okay, so we get that t a r squared 1, I'm going to write now b is bxr evaluated in x is bigger than or equal than e to the minus 5. Lambda is 1 over r, phi of 1 over r, comma a r squared, minus e to the minus r, minus 1. Now let's write down this thing. So phi is written here. I've chosen lambda to be 1 over r, so this becomes equal to e to the minus 1 over r. Lambda is 1 over r, so minus 1 over r squared, integral between 0 and a, r squared, and then we have g of 1 over lambda squared tau d tau. Let me put the dilation invariant measure on the outline. So I put the d tau over tau, and then I multiply by tau, so I'm done anything. And now let's make a change of variable here. So let's set, lambda is 1 over r. So I get r squared over tau here. Let's get rid of this guy here. Lambda has been chosen. It's so we get r squared over tau. So now let's make a change of variable. Let's set s to be r squared over tau. So ds over s is minus d tau over tau, because dilation invariant measure doesn't change. Okay. So when tau is 0, s goes to plus infinity. When tau goes here, s goes to 1 over a. So this becomes equal to e to the minus 1 over r squared, and then we get the integral between a to the minus 1 and infinity. Tau is r squared over s, so r squared over s. Then we get g of s, d tau over tau. Of course there is a minus here, but I flipped the endpoints. He's getting upset because I'm giving too many details, but this is the crucial point. Are you upset with me?
Maybe before exponent of integral we have inequality.
Where?
Before.
Where?
In the, we have integrals, exponent of integrals.
I have this bigger than or equal than this.
Yeah, and
then I have that thing is equal to this, and there is minus e to the minus 1 equal minus e to the minus 1. Everything is fine. Okay? So, at this point, I want to choose A sufficiently small. So, first of all, now I'm going to take, so the game is over now. Look at this. Okay? Maybe here there is, I changed from tau to S, so I apologize, there is S. Now, function gs over s squared is integrable at infinity. Why? Because gs goes like square root s. So this goes like 1 over s to the 3/2, which is integrable. It's in L1, near infinity. So function 1 over s squared times gs is in L1 of 1 infinity. So by Lebesgue-dominated convergence, if I let a go to 0 plus, this integral goes to 0. Okay? So, and at this point, all I want is to right. So at this point, all I want is so the integral goes to 0, so this quantity goes to 1. Okay? So 1 is going to win over this guy. Right? So it's enough that I take k, I take my number k to be 1 minus e to the minus 1 over 2. Absolute constant. Then I can find an a between 0 and 1 for which this quantity here is bigger than or equal than k. End of the story. And I must also have killed the break, right?
Yeah.
And you were very patient and very kind and did not stop me. I apologize, but I'm not used to this system, so I forget.
Yeah.
I get excited about the proof. So anyhow, is it clear what is going on now? You know, I have, so this quantity, as a goes to 0 plus, goes to 1. So the limit of this as a go to 0 is 1 minus e to the minus 1. So therefore, if I take k to be half that number, certainly I can find an a between 0 and 1 such that this quantity here is above k. And that's the end of it. Any question, Nasty?
I just understand.
So this is the one that goes to 0. And so this goes to 1.
Because g of 0 is 0.
Yes. And the good thing here is that nothing depends on x and r. X and r are, so the estimate that we're getting in the end is uniform in x and r. Because as you see from here, r has disappeared. If I had r in here, I would be dead. But fortunately, they are killed. Okay, so it's absolute numbers at this point. And just the fact that function g divided by s squared, because of this behavior at infinity, is in L1. So it's just Lebesgue-dominated convergence. All right, so now we will completely switch gear once again. And so I will devote the time that we are left today to start giving you an idea of what I want to discuss. I mean, it's of course, you know, the main motivation for everything that I've been talking about so far was not so much producing a different proof of known results as much as testing a certain circle of ideas with the perspective of moving on to a situation, to a setting which is more general than the Riemannian setting. And this is what I would like to illustrate now in the time that I've left. I will not be able to go into any, I will promise I won't go in any technical, really serious technical details like I've done so far, because I've already done that. So now I'm going to be moving to the setting of sub-Riemannian manifolds. And it will not be all sub-Riemannian manifolds. There will be special classes of sub-Riemannian manifold, but they will be general enough that will constitute an interesting extension of the results that are known in the Riemannian case. So, and I will mainly present a survey of the main results. So I will not, and from now on, I will not do any hardcore calculations anymore. So you can just sit back, relax, or let me talk. Leave me alone talking at the platform. So I hope that this will be interesting enough for you. So I will start now. So I will now move to the setting of sub-Riemannian geometry. And I want to show you, without going into any technical details, as most of the ideas that I presented so far can be generalized to at least some very large classes of sub-Riemannian manifolds. And then I will indicate some open problems which are not easy but are very, very interesting and very challenging. Okay. So let me start with M. M will not be a Riemannian manifold for me. M is just a smooth manifold. I will not put a Riemannian metric because I want to play with sub-Riemannian geometry. So M will be a smooth manifold, and I assume that on N I'm giving a second order diffusion operator with real coefficients and satisfying some appropriate assumptions. So I'm going to assume that M is also endowed with a smooth measure, mu. It does not need to be the Riemannian measure, it can be any measure, but the measure mu is going to be connected to operator L. Okay? So first of all, L01 is 0. So I don't want zero order terms in any local representation of this operator. Okay? Secondly, I want L to be formally self-adjoint with respect to mu. So that means that the integral over M of FLG, the mu, is equal to the integral of GLF, the mu, any f and g in C0 infinity of M. And I want L to be a negative operator. So I want f times LF d mu to be less than or equal than 0 for any f in C0 infinity of M. You'll notice that this property here, an integration by part, guarantees that the gradient, when I will introduce the gradient, the Carré-Duchamp is no negative, is bigger than or equal than 0, correct? Mm-hmm. So I will just list these general properties, and I will also assume that L is locally sub-elliptic. Now this is a serious assumption. Locally sub-elliptic means that, you know, there is this L satisfies an estimate of this kind. Well, first of all, let me introduce a Carré-Duchamp. Carré-Duchamp is, I will mimic what we did for the case of the Laplacian. So 1/2 L of f squared minus 2f LF. This is Carré-Duchamp. I will call it Carré-Duchamp. There is no vector field here, so Champ is just a very vague thing. And because of the assumption that I made here, this is bigger than or equal than 0 on any function. Okay? So this guy is bigger than or equal than 0, then let me assume local sub-elliptic for me means the following. Means that for any relatively compact subdomain of M, there exists constant C and epsilon depending on M. So depending on, sorry, omega, such that the H epsilon norm of F with respect to the mu squared is less than or equal constant times so here I have to put the square root of gamma F in L2 d mu plus so this is squared L2 d mu for any f in C0 infinity of omega. So this is called a sub-elliptic norm. The reason for this is that epsilon here can be a very small number. So when you're working with a uniformly elliptic operator L, then elliptic theory tells you that this epsilon here is a Sobolev space of order 2. So this is the fractional Sobolev space of order epsilon. And this number epsilon can be very small. I will give you examples. Okay? So these are the basic assumptions that I will assume, and I will assume much more as we go on. But let me discuss an example which is probably well known to all of you. So let me take R3, coordinates x, y, and z, and let me call G generic point in R3, and endow R3 with a non-commutative group law, which is this one. So G prime is x prime, y prime, z prime, and this is equal to x plus x prime, y plus y prime, z plus z prime, plus 1/2 x y prime minus x prime y. So R3 with this non-commutative group law takes the name of Heisenberg group. So it's a basic example. So R3 with this non-commutative group law is called the first Heisenberg group. The reason for the name Heisenberg group is not so much in the group law as much as it is in the commutation relation that comes from the Baker-Campbell-Hausdorff formula. So we see it immediately that if we define LG of G prime as G composed with G prime, so this is left translation, then the differential of the left translation is given by, so let's see, we get 1, 0, and minus y over 2. Then we get 0, 1, x over 2, 0, 0, 1. This is the differential of left translation. Okay? And therefore, if I define x at g as dLg of the standard. So this is the canonical basis of R3, ddx, ddy, ddz. So when you act on these guys, you get ddx minus y over 2 ddz. So then y of g, which is the differential left translation acting on ddy, gives you ddy plus x over 2 ddz. And then finally, z of g equal differential left translation acting on ddz. This is just ddz. Okay, so basic fact about, now if you identify these elements of the Lie algebra with left invariant, they are left invariant by definition, of course, left invariant vector fields, you immediately check that the commutator between x and y, which is x, y minus y, x, is simply ddz. So it's z. All other commutators, so x, z, yz, they are 0. Okay? So, because of this non-trivial commutation relationship, if we identify this with the position and this with momentum, then the commutation between position and momentum is the missing direction. This is Heisenberg commutation relationship of quantum mechanics, and therefore the group has been named by mathematicians. Heisenberg group, physicists know it as the Wise group. But mathematicians came in and they started calling it Heisenberg group, and the name is stuck. But physicists know it as the Wise group. So this is the Wise group for physicists. Of course, you can identify with a group of matrices, upper triangular matrices, but I will not insist on this thing. So why am I talking about the Heisenberg group in connection with this? Well, there is a notion of a diffusion operator on the Heisenberg group, which is L given by x squared plus y squared. So these two vector fields generate they bracket generate the Lie algebra. So we can define a so-called sub-Laplacian. This and this operator here, because of Ormander's 1967, so Ormander's theorem, there is a celebrated result by Ormander that says that when you have a sum of squares of vector fields, smooth vector fields, if the vector fields bracket generate the Lie algebra at every point, then the operator formed by taking the sum of the squares is a hypoelliptic operator. Hypoelliptic means that every distributional solution of L of u equals f is C infinity wherever f is C infinity. So if you take solutions of this equation in D prime, if f is C infinity, then this is not just a distribution, but it's a C infinity function. So this is a fundamental property of Laplace's equation, okay? And this property is shared by all these operators, which are called Ormander type operators. So they are operators which are sum of squares of smooth vector fields, under the assumption that the finite rank condition is satisfied. Since, you see, this is a sum of squares of two vector fields, and the vector fields trivially satisfy the finite rank condition because they bracket generate the Lie algebra R3. Therefore, this operator falls into this category, and therefore this operator, it is hypoelliptic. In fact, you can see that it's real analytic hypoelliptic, although that is a different story. But the important thing is, notice this operator fails to be elliptic at every point of R3. It's never elliptic. So the quadratic form associated with this operator, or if you wish, the eigenvalues of the quadratic form, one of them is constantly equal to 0. So you cannot control all directions. However, the redeeming feature is here. You can control the commutator, the missing direction. But that is a very complicated story. This theorem of Ormande is a deep theorem, so it's, I will not discuss it at all. So I will assume that my operator is locally subelliptic, so that it satisfies a subelliptic estimate of this kind. By the way, some pioneering work on this class of operators was done, at the time it was the Soviet Union, by Olenik and Rakievich. Olenik and Rakievich wrote a book, a beautiful book, on this type of operator, on subelliptic operators. And
may you write down this name?
this is Olga Olenik.
Oh, Olenik. Olga Olenik. Oh, I know.
Yeah, I'm sure you know. But it's my bad Russian. That Olenik and Rakievich. So they wrote a beautiful book in the late 60s or early 70s, in which they did some pioneering work on this type of operators of this kind. Okay.
Excuse me, and we also have this integral inequality. It seems to me that the opposite maybe.
Which one?
No.
This one?
This one.
No, this one, this
For
inequality is correct, yeah. Okay. Maybe this.
Oh.
Yes, thank you. Okay. So, I want to assume this because I don't want to write the semigroup as this.
Yeah.
I want to simply write this. That's why I'm taking that sign convention. Okay. All right. So, but I think I should stop here now. And so this is just one. Let me finish by saying that this operator here does satisfy this subelliptic estimate with the epsilon equal 1/2. Okay. So. So this is just one example of a diffusion operator. The manifold is very simple. The manifold here is R3, but the operator does satisfy this estimate, and you know, if you take the correct sign, it satisfies all these things here. Okay? So that's one basic example, but I will give you many more examples of this class of operators, and we'll move on from there tomorrow. I'll give you, not tomorrow, Saturday. For whoever is here, I'll give an overview of the results which can be achieved.